Okay. So far we have covered quite a lot in this class. Actually, we have finished chapter 4. We don't have many lectures left. We have this week and next week. So I'm going to talk about a bit in chapter 5. I won't be able to finish everything, but I'm going to just cover some key points. So chapter 5, the whole motivation is that we want to design a controller to stabilize a system, a open loop unstable system, right? So we had a method, in chapter 3 we introduced this hole placement method. So if we have a P given and P with order n, okay? That means the n might be high order system. We know how to design the CS. So that the order, so that with order n minus 1, so that the closed loop system is stable. So we know how to do this. We can do pole placement. Actually, you have tried this method in your experiment. But sometimes I just feel that this order for the controller might be too high. If this PS is fixed order, then you have to have a controller with fourth order in order to design the controller in this method, the pole placement method. Yeah. This is the pole placement. Pole placement. What if we say, we know that this order actually is the lowest order, so that you can do arbitrary pole placement. In order to stabilize the system, you don't have to do arbitrary pole placement, right? You just want to move the poles to the left-hand side of the comfortable. That's what you want to do. So it's conceivable that if you only want to do stabilization, you don't need this kind of order. That might be too high. A high order controller is not so good because you have to, it's difficult to implement, and it requires the computation power of the computer to implement the controller. You want to have a controller as simple as possible. So what is the simplest controller you can achieve? You can have? Well, it's just a P controller. Probably that's the simplest. It's just like a proportional controller. Right? So you are interested in whether we can, design simply a P controller to stabilize a given plug. You ask this question. If you can. Or if you can do that, of course, it's a good news. It's just you try to design one. So that actually, in this lecture, I'm going to tell you how to design such a controller. But occasionally, maybe very often, you cannot. Right? For example, if you want to control the inverted pendulum on the magnetic suspension system, you cannot use P controller. Then you need to ask the question: what is the lowest order of controller you can design so that the closed loop system is stable? That's such a question. Actually, this is a long-term, long-standing, open question. Nobody can answer that question completely. It's a complete satisfaction. So actually, the researchers have spent years and years to try to figure out the lowest order controller to stabilize a given plant. We're not able to answer that question completely either. We want to somehow partially answer that question. You know, so we try to see in a lot of cases, you know, we try to design a low order controller as low as possible, so to stabilize the system. Okay, so this the method is called a rule locus method, or rule locus technique. So we are going to see how we can do that. So this method was invented by this guy, right? Yeah, Evans. So the whole idea is that you know, we are interested in the poles of the closed loop system. We want to make sure that the poles of the closed loop systems are in a electrostatic constraint. Yeah. So when you do stabilization, we also know the poles are the key factors in determining the performance of the system, closed system. Right? We look at you know, the second order system analysis. We see that you know, how the overshoot, for example, is determined by the pole locations. So you have to pay a lot of attention to the pole locations of the closed loop system. That's what it is. Okay. Then of course, you know, if you look at the closed loop system, right? You have a plant, you have controller, and then you have a lot of parameters, a lot of those coefficients. So you change those coefficients, you will change closed loop poles. It'd be nice to know the relationship, right, between the parameters and the closed loop poles. Then you can tune those parameters to achieve some sort of a desirable closed loop poles. But the problem is that if you have many parameters, you have many closed loop poles, the relationship is very complicated. So today we're going to look at the simplest situation where you only have one varying parameter, and then change this parameter and see, you know, how the closed loop poles are changed. Right? If this the particular one parameter is exactly the gain of the proportional controller, then you're actually, you know, trying to find the relationship of the gain of the proportional controller and the closed loop poles. Then that gives you a very good understanding, you know, how you can design the proportional gain of the controller, right? You know, that at least solve one problem we posed earlier, that how you can design the simplest controller to stabilize the system. In what case it's possible. And the parameter, instead of being the design parameter, the changing parameter or the varying parameter might be some kind of a parametric uncertainty. You know, it's not really the controller gain. It's some kind of a uncertain parameter or some kind of really time varying parameter. You know, because in physical systems you have a lot of uncertainty. So that's why you really want to study. Based on these two motivations, you want to study the relationship of one parameter in the system, and between this one parameter and the closure poles. Okay, so that you want the the closure poles are like a point in the compass plane, right? So. Yeah, so like this type of thing, huh? So if you change the parameter, the pose is going to vary. You change, you know. And it just the pose will become a kind of curve in the compass plane. So this curve is called the root locus. Okay. Yeah. Again, we have the closure resistance. So this is. The standard closure system stabilization, we put it this way, and then this is more like for regulation, but it's like a 2-degree freedom. No. It's a single degree freedom. This is a unit feedback. Okay, this is so basically these two systems are more or less the same. When you study stability, they are the same. Okay. So the loop transfer function is L. L is P times C. Alright. So you know the closure poles are given by the roots of the following equation. Basically, this plus this. You know that that's basically the closed loop characteristic equation. Written in rather not quite a standard way. So suppose that the PS is BS over S, and the CS is little q, little p, right? So put together, then you see that 1 plus PCS is equal to 1 plus yeah. So if you want this to be 0, then that's equivalent to AS PS plus BS QS is equal to 0. Right? So this form is probably more familiar to us. You know, we call this thing closed loop characteristic polynomial. But sometimes you also write it in this way, you know. So maybe later on we're going to use both ways to talk about closed loop poles. Okay. So, if you want to investigate the poles, the closure poles, you want this to be 0. So basically, the closure poles are those S, those comes number S, so that this is 0. Okay. Then you just if you can find the S is just a point in the compass plane. This is 0. You can put it another way. The LS is -1. LS is -1 is the same as 1 plus LS is 0. Alright. So now we let ls to be something like this. Okay? So this is a loop transfer function. You basically you put your P and C all together. And then you got the open loop poles. Those are open loop poles here. There's an open loop transfer function denominator is here. So open loop zeros are all here. And the K is a gain. Okay? So when I say this one particular varying parameter, I really mean this. So I always assume this varying parameter is K, is a gain of the open loop transfer function. Okay? So all the poles and the zeros, I assume that they are fixed. You might think, okay, this is a really particular case. But indeed, if this, if you consider this K as a controller gain, and this whole thing as the plant, well, this is indeed the controller parameter you want to design. So this special form of a varying parameter is meaningful. It's actually very significant. We also assume this gain to be from 0 to infinity. It's positive, basically. We don't assume it's a negative. Just make the analysis a bit simpler. And the most case, of course, is a positive gain, controller gain. So that means negative feedback, right? Just if you look at the previous figure, you see that we have a negative sign here already. So you have to put a positive number here in order to have negative feedback. That's why it's reasonable to assume that K is positive. Yeah. We need to study the closed through poles when K varies. That's our objective. So the key equation is L is equal to -1. So we want to find the S so that this L is equal to -1. Equivalently, we want to find the S so that this is 0. So basically, we want to try to understand that. In order for this to be -1, we see the magnitude of this has to be equal to 1. Right? It's one condition. The second condition is that the phase of this thing has to be -180 degrees. Is that right? Not necessarily -180 degrees is also fine. Or 3 times 180 degrees is also fine. So it's because this phase is not a single valued function, it's a kind of multi-valued function. So we say, okay, the phase has to be odd number times times 180 degrees. Odd number. Okay. Yeah. As long as these two conditions are satisfied, then we have this. So now, the problem becomes, we want to find the set of those S so that this is satisfied and this is also satisfied. Satisfy these two conditions. Okay? Find the set of such S. Hopefully, it's a kind of curve to come to play. The magnitude condition, okay. Remember that the L has a K in front, has a K as a gain. So I want you to remember this K. L is proportional to K. Okay. So if you say when K varies, if you vary your K, you can always make this satisfied, basically. Put it this way, you take the L and put it in here, you can always choose your k from 0 to infinity, so that this is satisfied. So that you can see that the magnitude condition is not really an issue. Right? It's not a really issue. Because you have the freedom in k, then you multiply your k, then you can achieve that. So the critical condition becomes the second one. You know? Basically, the problem becomes as follows. You want to find the set of S in the Compte plane so that this condition is satisfied for some k greater than 0, greater than equal to 0. Okay? But if you look at the face, you see the face actually doesn't depend on k. So the face is equal to, and again we look at L. Okay. So L is this thing. It's k times all these things. So what is the face of LS? The face of LS is the face of k, which is 0, because it's positive number, plus the face of this factor times the face plus the face of this factor plus the face of this factor minus face of this factor minus face of those things. Huh? Okay? So you see that we have the following equation. Face of LS is the sum of those faces in the numerator, faces of the factors in the numerator, minus the sum of faces in the denominator, the factors of in the denominator. Yeah. One key observation is that this face doesn't depend on k. And the face, you want the face to be this odd number times 180. Alright. So now the problem becomes, because this doesn't depend on k, so now our focus now is to find all the S in the Compte plane so that this condition is satisfied. So this is a key condition. Let's look at the example. So we have an L S of this form, 3 poles and 2 zeros. 3 poles, we have say, okay, we have 2 poles this way and 1 pole that way. And two zeros over there. So, if we are interested in finding those S, so that the face of this is an odd number times 180 degrees, well, how do you compute that face of that of the face of that for a particular S? Well, we do the following. Okay, say we have an S here. We look at the face of this factor. Face of this factor is actually this angle. it's a S, right, minus Z1, S minus Z1 is this vector. Right? This is the face of that vector. You get that, then you get this phi1. Also, you have a Z2 here. The S minus Z2 is this vector. Huh? Then you get the this. Right? So this face plus this face plus this face. Okay, now we have consider all zeros. Now let's look at the poles. Okay. Poles you have okay. So for example, you have this pole. S minus this pole is this vector. When I say vector, I really mean a complex number, because complex number is in a two-dimensional space, so it looks like a vector. So the face of this vector, basically S minus P1 is this vector. It's alpha 1. Similarly, the face S minus P2 is this vector. And P3, face P3 they have alpha 3. So minus alpha 1, alpha 1. Then you say, okay, you get this the face of this guy. Now, so you know that this S is in the root locus. S is in the root locus. If and only if this is an odd number times, basically this is odd number times 180. So then okay, if you compute, it's not 180 degree or odd number times 180 degree. You say okay, this S is not in the root locus. If I haven't picked S, you compute this, and it is exactly 180 degree or odd number times 180 degree, then it's in the root locus. This sounds like a stupid way, You have to try all these points in the compass plane, and you still don't know how you can get the curve out. I mean, kind of of course, in principle, you can get the curve out. You just try to S and compute this way, then you probably can get the curve out. But that's still kind of silly. So, but the idea is like this. The principle, the idea is like this. So the concept behind this is like this, right? So we need to find out like a better way or like an easier way to get the set of all S so that this is a 180 degree, all number times 180. Okay, here comes the easy method. Especially if we don't want to get the exact root locus, we just want to get a rough idea of the root locus, get the kind of tendency of the root locus. You can use this rule to build the root locus. I probably want to have an example here so that we can go through those rules. By looking at a particular example, then it's probably easier to understand. Let's take a particular example from the textbook. So we have a loop transfer function. So this L, there's no zero. 3 poles. So you say the relative degree is 3. You know, the number of poles minus the number of zeros. That's called the relative degree. That's 3. You can also interpret this way. You say, okay, although there's no zero, no final zero, but you can say there are actually 3 zeros at infinity. Why you can interpret it this way? You know what is zero? What zero is a S number, is a point in the counter plane, so that this whole thing is 0, right? That's 0. But now you see that you don't have a finite S, which makes this 0. But if you let S to be infinity, well, this is indeed, this is infinity, and this is finite, so it's 0. And then you have actually, you have more poles, 3 more poles than zeros, the number of zeros. Then it's probably reasonable to say that you have actually 3 zeros at infinity. You can also do that. So if you interpret the zeros and poles in this way, then the total number of poles and total number of zeros are the same, right? So you just you have a few zeros at infinity. That's that's somehow we often say, this transfer function, you have 3 zeros at infinity. Basically, 3 is a relative degree. So number of poles minus the number of zeros. Okay. So first of all, let's look at this. The root locus is symmetric with respect to U axis. It's one rule. You might say, okay, why this is true? Why this is true? Actually, this is easy because the root locus is a set of S, so that this is equal to -1. Alright. So if S satisfies this, then S, the transpose, also satisfies this. Is that right? You take the transpose in this side, then this side, it's a real number, so the transpose is same. So this has to be true. So that means, okay, I really want to plot the root locus, okay? Oh, sorry. Usually the root locus. So the root locus is symmetric to the real axis. If you have something here, then you will have something here. That's one thing. One rule you want to remember. So that's easy to remember. Okay. Another thing I want to mention is that when you see a transfer function like that, we always plot. First, we plot the poles and the zeros. We don't plot them, we mark them. Well, say we have a pole here. We have a pole at -4. We have a pole at -5. We have 3 poles. Okay? So 3 poles. no zero. So there's no need to mark zero. If there is a 1, 0, we usually use a little circle. We use a little circle to mark it somewhere. But in the case of no zero, okay? That's a first rule. And this rule we have the simple reasoning, the derivation there. So the root locus starts from n poles, from this poles, when k is equal to 0, and goes to the n zeros. When I say, well, in this case, when I say n zeros, what do you mean? Well, it means that the n finite zeros plus the infinite zeros. Right? So for this thing, because there's no zero, then you know that the root locus will start from this thing. Well, actually, it goes to infinity. But how it goes to infinity? Infinity actually they have all, like all the directions. You can go to infinity that way, this way, or this way. So then that's something we have to determine. Okay, in a while. Then you say, okay, why this is true? Why the second thing is true? We need to give a reason. The reason goes as follows. So the root locus, suppose that we have in general we have L, right, in that form. In general, we have L in this form. This is K. This is S minus Z1. S minus Zm. S minus P1. S minus Pn. So when you say S is equal to minus 1, what does that mean? It means that S minus P0 Pn plus K S minus Z1 S minus Zm is equal to 0. So, yeah, the root locus, so S is in the root locus if and only if this is true. S in the root locus if this is true. So when K is equal to 0, you see, what are the S so that this is true? Those are exactly the poles. Right? So you see that the root locus will include those poles. Right? When K is 0. When K becomes very big, that means when K goes from 0 to infinity, right? When K becomes very big, then you see that this part can be properly neglected. When you say this is equal to 0, simply means that the second term is 0. The second term is 0, of course, it's just S has to be one of the zeros. So the root locus will approach approach zeros. But of course, when k is not really infinity, but it's just a huge. So this is nth order polynomial. You should have n poles, not n roots. But if you look at count zeros, you have m of them. So where are the other roots of this when k is huge? Well, it turns out that those roots, some of them will be equal to 0. So it will be approximately equal to zeros, but some of them will be actually huge. It will be like a kind of an infinity. So that's why we say that the root locus starts from n poles and goes to the finite zeros or the infinity. How it goes to infinity, we are going to worry about that later. The third rule, the third point actually concerns the root locus on the real axis. So root locus basically is kind of curved in the compass plane. What happens in the real axis? That should be easier to deal with. Okay. The real axis. We say, okay, we look at the real axis in this part of the real axis. Okay. If we look at the point like here, and we compute the phase of this, right? So if we look at the phase okay. Yeah, okay, now I know what's going on. So basically, if you still remember this picture, you see that you have to worry about this thing. You have to worry about this phase. You also have to worry about no, not this one. Actually, this should be like this. Yeah. So if we just look at the point in this part, and we need to look at the phase of these from a pole to this point, right? Just like here. If you look at here, you take any s. Now the s in the real axis. You look at the vector from a pole to that point. Vector from a pole to that point. Look at the phase of this. You can see that if this pole is in the left-hand side of the point, then this phase is 0. Right? You take another pole, you get the same thing. The phase is 0. You get another pole, phase is 0. If you happen to have a 0 there, you also need to look at this. From 0 to that constant number, you look at the phase. Again, if the phase, if the 0 are on this side, the phase is 0. The phase is 0, then you add them together or subtract them together, you always get 0. So in this case, you see that at this point, if you plug this point into here, the phase is over 0. It's not 180 degrees, certainly. So this point is not in the root locus, certainly. What about this point? This point. This point, you know, again, you play the same. You play the same trick. Now I erase this. Okay, I know that. I know that this segment or this this ray actually from origin all the way to infinity, none of those points is in the root locus. Now let's look at this point. This point again, I draw a vector. Look at the face. That's 0. Draw another vector. Look at face. That's 0. So everything. So every poles and zeros in this side, in the right hand. No. What? This is the left hand side of the point. Does not contribute any phase to this thing. Okay? So, but what about this? This, well, you draw a vector this way, and you see that, well, indeed, here I have a 180 degree. I have a phase thing. So you see a pole in the right hand side of the point will contribute a 180 degree phase to L when this number plug into L is particular S. Let's simply call it S and LS. Yeah. So if you have a one pole in the right hand side, okay, so this particular S is indeed in the root locus. If you have two poles in this side, well, two poles, then you go contribute to 360 degree. Okay, that's not right. That means this is not in the root locus. What about if you have three poles? Alright, then you see that well, in that case, you'll get the 180 degree again. So from this kind of argument, we'll see that this part, everything in this part is in the root locus. Okay. Here, no, that's not. So from this pole to that pole, this between these two poles, the second, that's not in the root locus. Why? Because you have two poles in the right. So okay, here this part, that's again in the root locus. So from this analysis, you see that we can easily get the complete understanding about the real line. Which part of the real line is in the locus, which part is not. Okay. So now look at the third point. The third rule. The root locus includes all points on the real axis to the left of an odd number of open loop real poles and zeros. So you take any point here, you count the number of poles and zeros to the right. Okay. If the number, you add all the poles and zeros together, if the number is is odd, then this part is indeed in the root locus. Look at this point. Since you know, you look at the left, you count the number of poles and 0 on the real axis. You know, now you have 2, right? So it's even number, so this part is not in the root locus. Okay. From this example, you look at the poles, but actually zeros. You can more or less analyze same way. You see a 0 to the right actually contribute 180 degrees to LS. A 0 in the left doesn't contribute anything. So same as pose. In this regard, of course. Now we have actually obtained the part of the root locus. It's not a complete story. It's just a part of the root locus. From if you know put all these 3 roots together, then you see that the root locus starts in the poles. So it starts from here, starts from there, and then it moves this way when k increases. Okay, and start from here. It moves this way, so you can actually put an arrow. See. This line actually you can expect this line is going to extend to infinity this way into that direction. These 2 lines, when they go, they're going to meet somewhere, and eventually they are going to go to infinity. Actually, that's what you can conclude from these 3 rules. Certainly, these 3 rules are not enough. We need something more. As this is the 4th rule. As k goes to infinity, n minus m branches of the root locus approach asymptotically to n minus m straight lines called asymptotes with angles given by this expression. Okay. So this rule somehow captures how the root locus go to infinity. So of course, you know, you need to know how many branches of the root locus go to infinity. So actually, these many branches. So you have these many poles, you have these many zeros. You know, then you say, okay, we have n branches of the root locus. M of them will go to zeros. N minus m of them will go to infinity. So now you see that you have 3 branches. 1 branch this way, 2 branches this way, and then these two branches will go to infinity. This 1 branch will also go to infinity. The issue is how they go to infinity, in what direction they go to infinity. Actually, this rule tells you that they go to infinity in those directions, in those lines, the straight lines, captured by those angles. And the starting point of those lines, so-called asymptotes, is on the real axis at this point. Now let's just compute those things, and then we try to get the rule locus. Okay. Look at those simple terms. Then we have probably a better understanding. So we first need to compute the angles. We'll definitely have three angles because you know these are three asymptotes. N minus m in this example is 3. So 3 you want to get these three faces, so three angles. How to do it? You first let k to be 0, then 180 degree divided by 3. You get 60 degree, right? You get one angle. Then you let k to be 1. Let k to be 1, then there's 180 degree divided by 3. That's 180 degree, right? Okay. Yeah. So 60, 180. Then you let the k to be 2. 2, then 5 times 180 divided by 3. What do you get? 300, yes, 300. That's right. Then you can put more k's there. So you get three numbers so far, okay? 60, 180, and 300. What if you let k to be 3? If you let k to be 3, you compute this, you will get the same number out of these three. One of the three numbers, right? Of course, you remember that like minus 60 is equal to 300, and things that this is a kind of periodic thing, right? So this is a phase is is a kind of a periodic thing. So we got the 60 already. We got 180. We got 300. But if you plug 3 in, 2 times 3, 4. So if you say 0, yeah, 2 times 3 is 7 times 180 degree divided by 3. So what do you get? In this case, this basically is 7 times 60 degree. That's 420 degree. 420 degree is the same as 60, is that? So that means what you get here is the same as this. So if you put more k's in, you will get basically there's one of numbers here. So this is equal to actually 60 degree. Okay, now I got these three angles. 3 angles. That means I will have simple dots. One goes in 60 degree that way. One goes 180 degree this way. The third one goes to minus 60 degree this way. Okay. Starting point of the simple dots given by this. The sum of all poles minus the sum of all zeros divided by 3 in this case. So what sum of all poles? So we call the kappa. We call the kappa there. Is a sum of all poles minus 0 minus 4 minus 5. So minus 9. Right? Minus 0, that's not no 0. That's 3. So this is a minus 3. So now, basically, we have minus 3 is here. this starting point of asymptotes. We draw the asymptotes, okay? One in that direction. 60 degrees should be like a 180 degree is this another one. This. Now we got the asymptotes. So the meaning of asymptotes is that when k is big, this thing is going to approach this. And this branch of the rule locus already exactly matches this actually. So that's no problem. So then you can imagine that these two branches will start from here and meet somewhere. Then we'll go into the counterpart. You know, actually we'll have a non-zero imaginary part. We'll split. One will go towards that. One will go towards this. Okay. So that's a rough tendency we map. So you know, then you see that it's going to meet and split. Then we need to know where it splits. If we have that information, then roughly the rule locus is done. So we know where it splits. Then we say split, then go just that direction. So that's roughly the rule locus is obtained. So now the final thing is to get the splitting point. So we have to follow another rule. So actually here says obtain a quick stretch of the rule by using only rule 1 to 4. I don't think only rule 1 to 4 is not enough. We need to look at the following rule. This is a 5. 5 is so-called is about the breakaway points and the break-in points. Breakaway points and break-in points are the same points. Actually, there's no difference because when they break in, then immediately have to split, break away. You know, so it's just like you'll get it from here. The break-in at a certain point is split. So how do you get the break-in and breakaway and break-in points? We need to solve that equation. Look at here, the definitions of breakaway points. Well, the rule locus meet and split away usually on the axis. Break-in point, where does one meet and enter? Meet and enter. Well, I don't think that we need to be too serious about this. I mean, breakaway. In my understanding, breakaway point and break-in point are more the same. So basically, here says that these meet. That's called a breakaway. When it comes in and split, that's called a break-in. That's also fine, but I don't think that's kind of important. That distinction is that important. Anyway, so let's just say somewhere they meet and split. Okay, we need to find that point. So according to that equation, okay, we need to find that point. Basically, we find the point. Well, we take derivative of this and let derivative to be 0. That's That's the point when they meet. Why is that the case? Again, let's argue for the reason a little bit later. So let's just do the computation and try to complete this blue locus. We take the derivative, then what do we get? We get s plus 4. So basically, L derivative of s is equal to So if you probably want to write this into the polynomial form. So s to the third plus pi s squared plus plus 4 pi 20s. Yeah, this thing is equal to this, right? Now, if I want to take a derivative of this, what do I get? It's 3s squared plus 18s plus 20. So, you let this to be 0. Of course, you need to solve this polynomial. That means 3s squared plus 18s plus 20 is equal to 0. Okay. Then s is equal to what? Luckily, for this second order, this quadratic polynomial, we can actually use a formula, right? So say A, B, C. Then you know this is minus b plus minus square root of b squared, 18 squared, minus 4ac. 4ac is 4 times 3, 12 times 20. 12 times 20. Divided by 2a, 2 times 3. What do you get? What do you get? So, I don't know, do you have a calculator? What is 18 squared? 18 squared minus, so this should be like 240. 18 squared. 18 squared, tell me. 36. No, what? You solve this, huh? Okay, the thing inside is minus 36. That's a minus, are you sure? Minus?
I'm sorry, I'm wrong.
84. So this is minus 3 plus minus square 84. What's that? 84. 9984. Huh? Right? 9 point something. Huh? Whatever number. This is roughly 9 point, 9 point something. 9 point something. 9 point. Let's just say roughly 9.1 divided by 6.
Yeah.
So this is roughly 1 plus or minus. That's 1.5 roughly. 1.5 a bit more. Yeah. So you see that you get two numbers. Yeah, this is one number is roughly minus 1.5. Another number is minus 4.5. 4.5. Where's a 4.5? 4.5 here. Okay, I see. So you see that you get two numbers. You know that the breakaway point is one of the two numbers. One is at 1.5. This is 4. So roughly this is 3. Yeah, 1.5 roughly is somewhere here. Another thing is here. But there's no root locus here, so there's that cannot be the case, right? So you ignore that one, ignore the minus 4.5, keep this 1.5. You know that this root locus is going to split from here. Now I have a very good understanding of the root locus now. So it goes from here and meets here, then split and then approach that thing. Approach that line. So it goes like this. It goes like this. Okay? So it's symmetric to the real axis. Right? One branch goes up, one branch goes down. So finally, I have a rough root locus. You never need to actually plot exactly. Nowadays, if you really want to plot this exactly, use MATLAB. MATLAB tells you. Actually, we just it's going to give you the exact plot. In this hand computation, we just get the raw values. Yeah, the green line. So we know that that when k is equal to 0, the root locus starts from here. K is equal to 0. K is equal to 0. And when k goes to infinity, k goes to infinity. Yeah. So what can we say? If we have the root locus, what can we say? What we can say is that when L is of this form, this is open loop transformation. The closed loop poles are in the root locus, are here and there, or there. When k is small, actually the closed loop poles are near here. When k is huge, the root locus are there. When the k is intermediate, of course, they are just like that. You can also figure out what is a particular k which makes this root locus split. Okay, you can actually figure that out. That should be that odd. So, if indeed your k is the controller gain you want to design, okay, then you can actually try to choose this particular gain to put the closed loop poles in the right place, roughly in a good place. The closed loop poles, so should be try to be like further away from the imaginary axis, right? Should be like towards that direction, when you design controller, right? You don't want the closed loop poles to be somewhere here, That's definitely bad, right? You don't want the closed loop poles to be very near this guy. That's also bad, right? So what can you do now is that, okay, if I say my closed loop poles, the desirable closed loop poles are maybe somewhere here, somewhere there, then you can indeed find the design that K match the closed flows. You know that the closed flows must be somewhere here. Cannot be there. Never be there, right? So that's why this just gives you the relationship of this particular parameter and the closed pose. So this can use to be as a guide in your design. Okay, so that's roughly what I can say today. So for that rules, of course, they all have reasons why this gives you the breakaway point. The derivation, I didn't have time to give the detailed derivation today. Maybe next lecture I'm going to tell you more about this, including some of the reasons behind the rules. Okay. Yeah, thank you. See you on Monday.